Examples of infinite sets introduction. So far we've been discussing the idea of infinite sets, sets that just go on forever, containing an uncountable number of elements. Now, to really make sure we understand what that means, we're going to look at some specific examples. Think of this as putting the theory into practice. On this slide, we're going to focus on three important sets of numbers: the integers, the even numbers, and the prime numbers. We'll carefully examine each one and explain why they qualify as infinite sets. We'll show you how, no matter how large a number you pick within these sets, you can always find a larger one, proving they continue indefinitely. In the following slides, we'll dive into each of these sets individually, so get ready to explore the fascinating world of infinite numbers. The set of integers. So let's move on to our first specific example of an infinite set, the set of integers. As you recall from the introduction, we're looking at sets that go on forever with no end. Now, what are integers? Well, integers are simply whole numbers. That means numbers without any fractions or decimals. They can be positive, like 1, 2, 3, and so on, negative, like -1, -2, -3, or even 0. We use a special symbol to represent the set of all integers. It's written as Z, and it's a bold capital Z. Mathematicians often use specific symbols to make things concise, so remember that whenever you see that bold Z, we're talking about all the integers. Let's list a few to get a clearer picture. If we start from the negative side, we have -3, -2, -1, then 0. And then moving to the positive side, we have 1, 2, 3, and it continues in both directions. We can represent this with ellipses, those 3 dots, to show that it goes on forever in both the positive and negative directions. Now, here's the key point that proves this set is infinite. Notice that for any integer you can think of, you can always find another integer that's either bigger or smaller. For example, let's take the integer 100. We can easily add 1 to get 101, which is larger. Or we can subtract 1 to get 99, which is smaller. And this isn't just true for 100, it's true for any integer. This process of adding or subtracting 1 can continue indefinitely in both directions. Because we can always find a larger or smaller integer, there's no largest integer and no smallest integer. Therefore, the set of integers is infinite. It just keeps going and going without ever stopping. This is a fundamental example of an infinite set, and we'll build on this understanding as we look at other examples like even and prime numbers in the following slides. The set of even numbers. So, what are even numbers? Well, even numbers are simply integers. Remember from the last slide, integers are whole numbers, positive, negative, or 0, that are perfectly divisible by 2. That means when you divide an even number by 2, you get another whole number with no remainder. Now let's represent this set. We can write it as 2, 4, 6, 8, 10, and then we put 3 dots at the end to indicate that this pattern continues indefinitely. Just like with the integers, we can always find a larger even number. If you give me any even number, I can simply add 2 to it, and I'll have a new, larger even number. For instance, let's take 50. If we add 2 to 50, we get 52. Add 2 to 52, and we get 54. We can keep doing this forever, right? And that's the key point. Because we can always find a larger even number, there is no largest even number. This means the set of even numbers is, indeed, infinite. Now let's look at a more concise way to express this set mathematically. We can write it as 2n, where n belongs to the set of positive integers. Let me break that down. The n represents any positive whole number 1, 2, 3, and so on. We denote the set of positive integers as z with a plus sign superscript, which is read as z positive. So, 2n means 2 multiplied by any positive whole number. If n is 1, we get 2. If n is 2, we get 4. If n is 3, we get 6, and so on. This mathematical notation is just a compact way of representing the entire infinite set of even numbers. Let's move on to our next example of an infinite set, the set of even numbers. Keep this in mind as we move forward, because understanding how to represent infinite sets mathematically will be important when we discuss more complex concepts later on. The set of prime numbers. Let's move on to our third example of an infinite set, the set of prime numbers. Prime numbers are whole numbers greater than 1, and they have a very special property. They can only be divided evenly by 1 and themselves. So, for example, the first few prime numbers are 2, 3, 5, 7, 11, 13, and the list goes on. We've already established that the set of integers and even numbers are infinite, and you might start to think that maybe, just maybe, the prime numbers will eventually stop. After all, as you count higher and higher, prime numbers do seem to appear less and less frequently. However, this is where a really cool mathematical idea comes in. There is no largest prime number. This isn't just a guess. It's a proven fact, and it's known as Euclid's theorem. Now let's see why this is true. We're going to use a bit of a trick, a proof by contradiction. Let's assume, for the sake of argument, that there is a largest prime number. Let's call that largest prime number P. Now here's where it gets interesting. We're going to create a new number, let's call it n, and it's defined as the product of all the prime numbers up to P plus 1. So, n is equal to 2 times 3 times 5 times all the way up to P, and then we add 1. Think about what this means. This new number, n, is either itself a prime number or it is divisible by a prime number. But here's the key. It cannot be divisible by any of the prime numbers in our original list, 2, 3, 5, and so on, up to P. Why? Because if you divide n by any of those primes, you'll always have a remainder of 1. Therefore, if n is divisible by a prime number, that prime number must be different from any of the primes in our original list. This means we've found a prime number that's larger than P, which contradicts our initial assumption that P was the largest prime number. So, our assumption must be wrong. There will always be a prime number larger than any given prime number, and that means the set of prime numbers is infinite. This nicely ties into what we discussed on the first slide. Infinite sets have no upper bound. In the next slide, we'll recap these key ideas and also discuss some common mistakes students make when thinking about infinite sets. Key takeaways. Let's recap what we've learned about infinite sets with this final slide. Next, it reminds us that the set of integers, and I'm reading the symbol here as z, is infinite because you can always find a larger or smaller integer. We saw this in action earlier. No matter how big or small a number you think of, you can always add 1 or subtract 1 to get another integer. Then, it reiterates that the set of even numbers is infinite because you can always add 2 to any even number to get another even number. We built on that idea, starting with 2, then 4, 6, and so on, demonstrating that this process never stops. Moving on, it highlights that the set of prime numbers is also infinite, and this is a particularly interesting case because it's proven by something called Euclid's theorem. We actually walked through the logic of that proof, imagining a largest prime, and then showing how you could always construct a bigger one. Finally, and this is a really important takeaway, a key characteristic of infinite sets is that they have no upper or lower bounds. What that means is there's no biggest number and no smallest number within these sets. They extend endlessly in both directions. So, keep these ideas in mind as you continue your mathematical journey. Understanding infinite sets is fundamental to many advanced concepts, and we've laid a solid foundation here. Now, let's move on to look at some common mistakes students make when dealing with these concepts so you can avoid them. Common mistakes. A common mistake is to assume that because prime numbers become less frequent, there must be a largest prime number. Now, we've just spent time establishing that the set of prime numbers is infinite, and a natural intuition might be to think, well, as you go higher and higher, prime numbers seem to appear less and less often, so surely there must be a biggest one. But remember Euclid's theorem, which we discussed on the previous slide. It rigorously proves that no matter how large a prime number you find, you can always construct another one. So, the decreasing frequency doesn't mean they stop existing. It just means they're spaced further apart. Don't let that decreasing density trick you into thinking there's an end to them. It's important to remember that even though the density of prime numbers decreases, they continue infinitely. This point reinforces what we just discussed. Density refers to how closely packed the prime numbers are. As numbers get larger, the density of primes gets smaller, but they still go on forever. It's a subtle but crucial distinction. Another mistake is to confuse finite and infinite sets. If you can count the elements in a set, it is finite. If you cannot, it is likely infinite. This is a really important general principle. Think about it this way. If you have a set with, say, 5 elements, you can list them out 1, 2, 3, 4, 5, and you're done. That's a finite set. But with infinite sets like the integers, even numbers, or prime numbers, no matter how long you count, you'll never reach the end. You can always add one more, or find another element. So, the ability to potentially count all the elements is the key difference between a finite and an infinite set. If you can't, it's a strong indication that you're dealing with an infinite set. Let's move on to the final slide, which highlights some common pitfalls students often encounter when dealing with infinite sets. And that brings us to the end of this section on examples of infinite sets. Remember these key ideas, and you'll be well equipped to tackle more complex concepts in the future.